Hello and welcome back, humans. I'm Jason, and today I'd like to talk about a topic that's about as old as humanity itself and yet still full of mystery and wonder. What exactly is fire? It seems like a really simple question because we've all seen fire. We pretty much know what it is, but what is it exactly? Specifically, why does it glow the way that it does? Why does a flame dance around? And why does a flame have a teardrop shape to it anyway? Also, why are most flames orange or blue, but not pink or purple? And why does it take heat or friction, such as when you strike a match, to actually start a fire? Now, fire is one of those phenomena that we encounter almost daily, yet how many of us truly understand what it actually is? When we strike a match, or if we light a candle, what exactly are we witnessing? Well, today we're going to unravel the fiery mysteries of fire, from the flickering flames to the chemistry and the physics that make it all possible. Now let's firstly back up the truck a little bit and talk about what is it that we see when we actually see fire. Fire is a visible manifestation of a chemical reaction called combustion. We've all heard of combustion. Now, combustion occurs when a fuel reacts with an oxidizing agent, usually it's oxygen in the air, and that produces heat and light and various reaction products like carbon dioxide and water vapor. Now, almost all organic substances, when they burn, which means when they combine with oxygen, will produce carbon dioxide, CO2, and water, which is H2O. Now, depending on exactly what you're burning, you can obviously have additional products, but if you have complete combustion of organic substances, usually that's what you're getting: carbon dioxide and water. Now, carbon dioxide is CO2, but if there isn't enough oxygen available for complete combustion, then you might get carbon monoxide, which is CO, one atom of each, instead of the CO2. And in many combustion reactions, you actually get a whole host of products. You'll get a little carbon dioxide, you'll get a carbon monoxide, you'll get the water, and you'll have a lot of other unburned products like soot and other things that are not completely combusted, oftentimes, for instance, in a campfire. Now, combustion reactions in chemistry form carbon dioxide, CO2, and water because these are extremely stable molecules, which we say are in a low energy state. And that means that the configurations of electrons in those molecules are in a lower energy state than the fuel before they were burned in the burning process. Now, before we go on, I need to talk a little bit more about the concept of energy in general. There's two main kinds of energy that we talk about in science. One of them is called potential energy, and the other is called kinetic energy. The kinetic energy is when things are moving. It's basically related to how fast everything is traveling. But the potential energy is exactly what it sounds like. It's what potential does this thing have to do some sort of work on something else. And if it has a higher potential energy, then we say it can do more work on something whenever that potential energy is released and converted into kinetic energy of movement. So the easiest way to think about that is think about a mountaintop. If you have a very tall mountain and you're standing at the top of the mountain, you're very high above the ground. So you have a large amount of potential energy. The ground, if you were to walk down the mountain in a controlled way and don't, kill yourself falling down the mountain, when you get to the bottom, at ground level, at sea level there, you would say that you are in a lower potential energy, maybe the lowest energy that you can be, because you can't fall through the ground, right? So the potential energy is the energy you have by virtue of your position in some sort of field. In this case, it's a gravitational field, but this potential energy thing, it applies to electric fields and pretty much any field in physics. So here I'm talking about gravity because it's very, very familiar to you. So your position at the top of the mountain is very high above the ground in a location in that field very high above the ground level, and we say that's a high potential energy state. Now at the ground level, at the bottom of the mountain, its position in the field is way down there. We call that the low energy state. Now, there's a fundamental law of our universe. You just have to swallow it and accept it. In general, things like to move from high energy positions or high energy states and they like to go to the low energy state. You could ask, of course, why does that like to happen? And we don't have answers for that. We just know that that is the way our universe goes, and it's tied to the concept of entropy, and it's tied to the concept of the direction of time flowing in our universe. Time seems to flow such that, on the aggregate, systems in general like to go from high potential energy to low potential energy. So if I'm standing at the top of the mountain, then if I were to tip myself over the edge, then of course my body will like to fall, because we call it the force of gravity, but it will like to move from a position of high potential energy to low potential energy. We take this for granted because we know that when we jump off the top of a building, we're going to fall, right? But we only take it for granted because our entire universe operates this way. So try not to think about common sense. Try to put that in the back of your mind, and we're going to apply it to something else. All of these chemical systems, when it comes to burning things, the configuration of the electrons in the fuel and the oxidizer, the oxygen, beforehand, those electrons surrounding those molecules are in some potential energy configuration. If you remember back to chemistry, you were taught that electrons exist in orbitals of different energy. You have the energy level number 1, energy level number 2, which is farther away, energy level number 3. It's kind of like the whole mountain analogy. And the higher the electron is, we say it's in the higher energy state. And these electrons, if they can, they love to go down to the lower energy state. But they can't if there's already electrons down occupying those low energy states, because again, in chemistry, you learn that you can only have so many electrons existing in each of these orbitals. And if they're full, well then tough, you just can't get down there. Right now, in a chemical reaction, all that is happening is the electrons are moving around from one substance to another. In the case of this piece of paper here, it consists of lots of carbon compounds in here. There's cellulose in here, wood in here, all kinds of things. There's carbon, there's hydrogens in here, oxygens in here, a very complex molecule in here. And the electrons that are in this configuration are in what we call a higher energy state, because it's a complex molecule that is interconnected with chemical bonds, and so the molecular orbitals in general are a higher energy state. Now, surrounding this piece of paper is oxygen. And the oxygen that exists in the atmosphere is not a single oxygen, it's O2, which means 2 oxygens bonded together. So that oxygen exists with the electrons in that oxygen molecule in a relatively higher energy state. Now, the oxygen is stable. It doesn't spontaneously break down. The paper here is stable. It's not spontaneously wanting to do anything. It is stable. It is just that these configurations of electrons, we say, are in slightly higher energy. Now, if I could get this oxygen atom to go and interact with the complex molecule in here and switch electrons around and rearrange the atoms that are in here with the atoms of the oxygen and trade electrons and share electrons in a different way, if I could get it to do that such that the final configuration after the burning is a lower energy state of the electrons, you can think of them falling down into lower orbitals if you want to think of it that way, then the system would like to do that. Why? Because it's in a relatively high energy state here, like at the top of the mountain, and after burning, it's in a much lower energy state. So when I say that water as a molecule and CO2, carbon dioxide, as a molecule are in a low energy state, what I'm literally saying is the configuration of the electrons in those molecules have, when you add it all up, is a lower energy, the lower potential energy, than the configuration of the electrons in this complex molecule beforehand. And the universe always wants to go from high energy to low energy. And so that's what happens. The burning happens and the rearrangement of the electrons happens, putting it in a lower state. And that's why burning, quote unquote, likes to happen, right? But the question you have to ask yourself is, okay, well, if it was in a higher energy state to begin with the paper and the oxygen, and then it goes into a lower energy state after burning, CO2 and H2O, right, which is very, very stable, very, very low energy state. Okay, if it started at high energy and it ended at low energy, where did the excess energy go? Well, ask yourself the same question. If I'm at the top of the mountain, I have high potential energy. If I jump off and I go to the bottom of the mountain, I suddenly have low potential energy. Where did the energy go? Well, I tumbled all the way down the mountain, and my potential energy at the top of the mountain was converted into mechanical or kinetic energy as I rolled down. In other words, it went into agitating my body and tumbling. It went into kinetic energy. And I got to the bottom, but I was rolling with a very high velocity at the bottom. And so it was converted into the energy of movement. We call it kinetic energy. So the same thing is happening with burning. When I burn it, the electrons are rearranged, the atoms are rearranged into CO2 plus H2O, right? And the energy that it was locked up in here before gets converted in the burning process into movement of the atoms. And we call that heat. It also goes into light, which we're going to talk about in just a second. That's what we see when we see the burning. So the energy from the high potential energy state goes into light, which we see in the burning process, and it goes into heat. That's why campfires are hot. That is what is happening when things burn. So when you actually look into a flame, like for a campfire, what you're really observing is the rapid oxidation of a material. In other words, it's burning. And the heat generated by the chemical reaction causes the gases that are produced to glow and emit light. This glowing is what we actually perceive as fire. I want to talk a little bit about what we perceive as light. You have two eyeballs and you have photoreceptors in the back which are sensitive to a tiny, tiny, tiny part of the electromagnetic spectrum, photons of a certain energy range, right? The colors of the rainbow. You don't see infrared and you don't see ultraviolet and you don't see gamma rays and you don't see X-rays and you don't see radio waves, but you see this tiny, tiny, tiny band of energies of photons that we were evolved to eventually see, because why? Our sun is bathing the planet in this all the time, and that's what's readily available. That's why our eyes are sensitive to those particular wavelengths and frequencies of photons. All right. Now, where do the photons come from? If you take a piece of metal and you put it in a campfire or on a flame, eventually the metal will get hot, and the metal itself will not necessarily burn unless you make it really hot. You can burn metal, of course, but it will glow. And it'll glow long before it begins to do any chemical reaction. Why does it glow? Well, because if it's iron, let's say, then there are lots of electrons hanging out there, and when you heat it up, you physically are shaking the atoms. That's what it means to heat something up. And the electron cloud consists of lots of electrons, and when energy goes into that electron cloud, one of the electrons will absorb some energy and go up into a higher energy orbit, higher up the mountain, so to speak. And then remember I said electrons always want to come back down in energy as fast as they can, so they decay down. And when they go from that higher energy orbital to the lower energy orbital, what happens? It emits a photon. The energy difference when it decays down is emitted as a photon of light. So when we see the red glowing of metal in a campfire, if you heat it up, right? Like some kind of foundry or some kind of molten metal or something. What we're seeing is the electrons shaking, and they're basically decaying back down, and they're emitting photons. When we burn something, what's going on is the electrons are rapidly rearranged as the atoms are also rearranged into the products of usually CO2 and H2O. But of course, I said you can get carbon monoxide, you can get other products, but in general, CO2 and H2O are really, really common. And when the electrons decay down into their final state, they're going into lower energy state, and they are releasing electrons as well. Now, in that process, when they're not releasing electrons, the electrons are decaying and they're releasing photons. So those photons leave the system as light energy, and we see that. But also, some of the energy, as it goes from high to low, is going into agitating and physically moving the atoms, and that makes it hot. And so that heat is what we feel, and that heat further feeds the reaction, because as we know, it takes a spark to start a fire, right? But once it's started, it's kind of a chain reaction, not a nuclear chain reaction, but just a chemical chain reaction. The heat generated as the reaction proceeds, right, is what continues to make the reaction happen. And so that's why things burn until the fuel is gone, because the heat that's generated goes into continuing the burning process. And the colors of the fire that we see are going to come from the specific atoms that are burning, and also what energy levels the electrons are jumping between when they're agitated, right? So you might think of natural gas burning with a beautiful blue flame, and you might think of fire burning with that awesome orange warm glow, right? Well, that comes about because it comes about from a lot of things. The heat of the fire, the fuel, because methane or whatever you're burning in the natural gas, the propane, butane, methane, whatever you're burning is going to have electrons in a certain energy level. And when they burn, they're going to pop up and then decay down with a certain frequency and decay and emit photons of a certain color. And wood is doing the same thing, but the molecules that are inside of wood, the electrons are going up and down and releasing a slightly different frequency of color. So the different colors are just coming from the different materials you're burning having electrons in different orbits and jumping up and down in a different energy state, releasing a different color photon. We generally don't see pink and purple, although you actually can if you burn the correct chemicals to have electrons to jump between the proper energy levels. You can have pink and purple fires, but it's rare based on the common materials that we have around us burning. Usually we see oranges and blues most of the time. Now I'd like to talk about something crucial in this whole process. Burning isn't really just as simple as adding oxygen to fuel. There's a specific set of conditions you all know about in order for combustion to occur. And so this brings us to our next topic, the energy needed to start the reaction. I mentioned before I have this piece of paper and the configuration of the atoms and electrons are in a relatively higher energy state here. If I could burn it with oxygen, we already know it's going to burn. Heat and light are going to come out of this thing and it'll turn to some other there'll be some ash, there'll be some carbon dioxide, there'll be some water, and so that will be the final energy state, right? But let me ask you a question. If the universe likes to travel from high energy state to low energy state, like rolling down the mountain, then why doesn't this paper just go ahead and burn right now? If it's already in a higher energy state right now, which is what I'm telling you, along with the oxygen, and in the final energy state, CO2 and H2O, I'm telling you, is a lower energy state, that's a fact, okay? Then why doesn't this thing just burn right now? And the answer is as simple as thinking back to our mountain. If you're standing on top of the mountain, why don't you just fall down spontaneously? Well, the answer is, I'm standing at the top of the mountain, and the top of the mountain is a little bit flat at the top. There is a stable region at the top upon which I can stand, and I'm not going to be pulled to the ground because it's a stable area. You can think of the top of that mountain being maybe a little valley or a little, not a crater, but a little depression in the top, right? Or a bowl with a marble in it. If you put a bowl and put a marble inside of it, the marble, even if it was at the top of Mount Everest, is going to stay inside the bowl. But if you have a bowl on top of Mount Everest with a marble in it, if you push the marble up to the edge, giving it energy over the lip of the bowl, then down the mountain it goes. But it's not going to do anything unless you give it enough energy to get over the hump. So this is called activation energy, and this is what I want to talk about next. You have to give this system a little bit of energy to get started so the reaction can proceed. And then once it begins generating its own heat, then the activation energy for the next atom to burn and combust is provided by the previous atoms that have released some heat when they combusted just before. So the fire burns along the paper from one edge to the other, and this chain reaction is happening as the whole paper then gets combusted. So another way of saying this is that to kickstart combustion, you need a certain amount of energy to get going. We can call it the kindling temperature, but we often call it the activation energy. This is the energy required to break the initial bonds in the molecule so that they can rearrange and form bonds in the product. You can think of it as the spark that sets the whole process in motion, and once the reaction starts, it releases energy, heat and light, which sustains the process, allowing it to continue as long as there is fuel and oxygen available. Now, as the fire burns, here's a question for you that's often asked. Is fire a plasma? Plasma is one of the four fundamental states of matter. Alongside solid, liquid, and gas, there's also plasma. It's an ionized gas, which just means that enough energy has been added to the gas to strip some electrons from the atoms, resulting in a mix of positively charged ions and free electrons, which are negative, floating around with the gas itself. Now, while fire can contain plasma, especially in extremely hot flames like those in a welding torch or a lightning strike, not all fire is really considered plasma. The yellow and orange flames that we commonly see in a campfire or a candle flame are mostly just hot gases with some small degree of ionization, but not enough to really classify them truly as a plasma. This is kind of a silly question anyway, because calling something a plasma is really just a matter of degree. When we look at the sun, we know it's basically a ball of plasma. There's a very high degree of ionization going on because there's so much energy coming out of the sun. The electrons are often ripped apart from the atoms, and everything is a soup of charged particles, ions, protons, electrons, and sometimes the electrons are recombining with the protons and forming atoms and releasing light, and then they're getting ripped apart again, and there's what we call a very high ionization fraction, like in a true plasma, like the sun or a lightning strike. Because the energy is so high, a lot of what you're seeing there is ripped apart electrons, right? But in a candle flame or a very low temperature plasma, technically it is a plasma because there's a very small fraction of electrons which are, dissociating and then recombining. We don't really call it a true plasma, but really what's going on is the ionization rate is very low. So it is a plasma just with a low ionization rate. Same thing going on in those little plasma balls. Yes, there's a little bit of plasma in there. You're seeing the purple tendrils float around because the electrons are recombining with the gas and emitting light. So it is a plasma. It's just a low fractional ionization compared to a high energy system like a lightning strike or the sun or something, a nuclear fission or fusion reactor, something like that would have a higher ionization fraction. Now, the last thing I like to really talk about real quick is I like to explore exactly where the light comes from when we say and see things that are on fire. The light is emitted by flames due to two main processes. One of them is called blackbody radiation, and the other one is called chemiluminescence. Now, blackbody radiation occurs when hot gases and soot particles, whatever's being burned in the flame, emit light just due to their temperature. This is similar to how an incandescent light bulb works. Now think back to the incandescent light bulb, not the newer ones that are much, much cooler, but the old school one. It's just a filament in there, electricity runs through it. Nothing is burning inside of there, but it releases a lot of light. And that releases light through what we call black body radiation. What's happening is the electricity is flowing through the filament and it's causing friction from the electrons moving through the filament, and it gets hot. Anything that has a certain temperature, any temperature in the universe, emits photons. It's called blackbody radiation. The reason it's called blackbody radiation is because the frequency spectrum of the photons that are released depends on the temperature according to a blackbody law that was developed a long time ago. All it means is that everything at a given temperature emits a certain spectrum of light. All right? And when we heat up the hot poker in the fire, it glows with that orangish glow. But if we heat it hotter and hotter and hotter, the color of the glow changes a little bit because it depends on the temperature. My body right now is at some temperature above absolute zero, so I'm emitting photons right now, but you don't see me glowing because I'm glowing in the infrared. Everything around you is glowing in the infrared just because it has a temperature. And the reason things glow at a given temperature is because of the jiggling of the atoms and the jiggling of the electrons. When the electron cloud jiggles, and what I mean by jiggling is it gets energy, so the electron pops up. When the electron decays, a photon is released. So if you have any temperature at all, your electron cloud is jiggling, so to speak, and that releases photons. That's called blackbody radiation. And that accounts for a good chunk of the light that comes out of a fire, just by nature of its temperature. Now, there's something called chemiluminescence, which is a really fancy sounding word that basically happens when certain molecules in the flame are excited to higher energy states during the chemical reaction itself, during the rearrangement process of the electrons. When these molecules' electrons return to the ground state, they release energy in the form of light. And so this is responsible for some of the vibrant colors we see in flames, especially when we burn different chemicals. So, why do different materials burn with different colored flames? The variation in colors come down to the specific elements involved in the combustion process, as I mentioned just a minute ago. For instance, if you burn sodium, you get a bright yellow flame, while copper produces a greenish, bluish flame. And this is just because different elements emit light at different wavelengths when they're heated, because the electrons that are there are at different energy levels. And we already talked about the heat coming about from a fire. We have a fancier word for that. It's called an exothermic nature of the combustion reaction. When the fuel burns, the chemical bonds are broken and the new ones are formed in a lower energy state. This releases energy, which is what I said before. The energy heats the surrounding gases and that radiates heat. So to wrap it all up, fire is a complex interplay of chemistry and physics. It's a fascinating dance of energy, light, and heat, and it's a rapid oxidation process that produces heat and light, requiring a certain amount of energy, which we call activation energy, to initiate the burning and sustain it. This can be by a spark, by another flame coming close, by friction like striking a match, And while it can contain plasma, it's not always classified as a plasma, and the colors and the heat that we observe from the specific elements involved and the energy released during the chemical reaction. I'd really like to thank you for joining me on this fiery exploration of science. I appreciate you hanging out with me. I think personally some of the questions that most people would probably say are the simplest actually can yield a fair amount of understanding when you really dive into it. In fact, I'll go so far as to say there really are no dumb questions, and there's definitely no simple questions. If I ask you something super simple, I guarantee if we go deep enough, we'll get all the way down to quantum mechanics, and then it'll be sufficiently complex for anybody. So, until next time, stay curious, keep exploring the wonders around you. This is Jason signing off. Remember, always stay curious. Learn anything at mathandscience.com.